In this video, we're going to look at a required practical that is mentioned on the OCR Advanced Information for both Foundation and Higher, and that's a circuit to measure energy transfer. This could be a number of things, but it's likely to relate to heat capacity and heating a metal block, or possibly heating water, because the other practical that's mentioned is heating water, and I want to go into that in a separate video. But we're going to look in this video at how to measure heat capacity. So heat capacity is the energy needed to raise 1 kilogram of material by 1 degree Celsius. So we've got a 1 kilogram of metal here, and we obviously have a thermometer to measure the energy, the temperature change. And here, this is our electric heater, which is going to supply the energy to heat up the metal block. So we've also got a few other things here. We've got some insulation, and we obviously need insulation to prevent energy loss, which is the same reason that the heater does not stick out the top, because that would be energy loss to the room. And we also here have some oil, which is again to prevent energy loss to the air, because if we were, the heat has to go from the metal block into the thermometer. We don't want it to heat up the air, we want it to go straight in. So this reduces energy loss. Now you might also say, well, why is there no lid on there? So you could, equally put a lid on and insulate it above as well. So lid or further insulation, that would also be sensible. So what circuit do we need to do? Well, we need to understand what electrical energy is so that we can measure the energy going in. Electrical energy is current times potential difference times time. So in terms of our circuit, we obviously need a power supply. So this is our symbol for a battery, or it might be that this one is given for a power supply. We need to measure the current that is going through the heater. So current is measured in series, so we can draw an ammeter in series. And then we also need to measure the voltage or the potential difference, and that is measured in parallel across the heater. So we draw a separate branch to measure the potential difference. Now that's not the neatest circuit in the world, so we could redraw it in a slightly neater way with actual straight lines, and we could use the symbol for a heater. So this here is the symbol for a heater, and then we can show the voltmeter in parallel with the heater. So this is much neater, but it's exactly the same circuit as this. This is more of a picture, and this is the actual circuit symbol. Now there is an alternative way to do this, where we could simply have a power supply, and then we can use an object or a meter called a joule meter to measure this directly. So a joule meter might just be a box. I mean, that looks a bit crazy and messy. Sometimes you will see a joule meter like this. So here is the circuit symbol, where we've got our heater, we've got our joule meter, we've got our power supply, and the joule meter will measure directly the energy that is being transferred to the heater through the circuit. So either of these are okay. It's hard to predict what will come up, but certainly this one could. Now in terms of the results of this, or calculating heat capacity, the equation that is on your formula sheet is this. So we've got energy transferred is mass times the specific heat capacity times the temperature change, which means the heat capacity is the energy divided by the mass times by the temperature change. So once we know the electrical energy, that is being supplied, when we know the mass and the temperature change, it's really easy to work out the heat capacity. And of course, the electrical energy, if they choose to use this method, is current times potential difference times time divided by mass times temperature change. Now I suspect this is likely to be higher tier, foundation tier. This is what they might ask you, or it might equally just be a joule meter, or maybe it's just labeling the circuit and they might provide you with this equation. It's really hard to tell, but those are my predictions. Now, the other difficulty at higher tier, what they might say is, here are some results. Here is the energy being supplied against the temperature. So what is going to happen if we plot energy against temperature? Well, at the start, the heater's heating up, nothing happens. Then the heater heats up, but it takes time for the heat to conduct through the metal. So it takes time for anything to happen, and only after a period of time does the temperature start to rise. So you usually get a graph like this, where it starts very, very slowly, and then it eventually reaches a constant rate of temperature increase. So if they were to give you a graph like this, then we can work out the heat capacity from the gradient. And in this case, the gradient is 1 over the heat capacity times mass, which means the heat capacity is mass times heat capacity is 1 over mass times the gradient. Now, this is trickier, which is why it's probably only going to be higher tier if it comes up. If they don't give you any clues, you can either memorize this graph by heart, or you can use your maths, and you know that y equals mx is the equation for this part of the line, and you can match it up to here. So you know that x is energy, y is temperature, and so the gradient must be the other things here, which would be 1 over mc. But I suspect this is less likely to come up than a calculation like this. Let's just do 2 quick questions. So if you pause the video now and try both of these questions. So it says work out the heat capacity of the block. So specific heat capacity is energy over mass times by temperature change. So the energy supplied 1950. The mass is 2 kilograms, temperature change is 3 degrees Celsius. So 1950 divided by 6 gives us 325 joules per kilogram per degree Celsius, because it's joules per kilogram per degree Celsius. Part 2, which metal is it likely to be? Well, it's the closest to brass. This number is most close to brass, so it's likely to be brass. And if you had to explain it, you'd say, well, the heat capacity of brass is very, very similar to the heat capacity that we've calculated. Why are they different? Well, there might be some errors. There might be some energy loss to the room, maybe because there isn't a lid, or because we didn't use water, or because there was no insulation, and that might explain the difference.